Oh my gosh, you guys. We're having an experience here. I had to restart my streaming software and then it needed to update, and now we've got just over a minute until we get started here. Oh, and I need to turn on the light. Oh goodness. Let me make sure sound's coming through all right. Oh, we're doing beautifully. We're doing beautifully, ladies and gentlemen. No complaints. Oh, another day of admin of code. We're already up to day 8, so we're not quite a third of the way through, but almost. Which makes me kind of sad. I like doing this, and I don't want it to be over. Alright, so we got our file on the right here, ready to go. We got our instructions on the left, and we have 37 seconds until we get started here. Okay. Apologies for the small delay there. Some of it's weird. I just ate a strawberry and I think one of the seeds got stuck in my teeth. Had to fix it. Had to fix it. You know how it is. All right, we got the light on. 5, 4, 3, 2, 1. Day 8. Let's go. Day 8. Treetop treehouse. The expedition comes across a peculiar patch of tall trees, all planted carefully in a grid. The elves explain that a previous expedition planted these trees as a reforestation effort. Now, they're curious if this would be a good location for a treehouse. First, determine whether there is enough tree cover here to keep a treehouse hidden. To do this, you need to count the number of trees that are visible from the outside of the grid when looking directly across a row or column. The elves has already launched a quadcopter to generate a map with the height of each tree, your puzzle input. For example, a grid. Each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. A tree is visible if all of the other trees between it and an edge of the grid are shorter than it. Only consider trees in the same row or column. That is, only look up, down, left, or right from any given tree. All of the trees around the edge of the grid are visible. Since they're already on the edge, there are no trees to block the view. In this example, that only leaves the interior 9 trees to consider. Right, that makes sense. The top left 5 is visible from the left and the top. It isn't visible from the right or the bottom since other trees of height 5 are in the way. The top middle 5 is visible from the top and the right. The top right 1 is not visible from any direction. For it to be visible, there would need to be only trees of height 0 between it and an edge, which there aren't either north or east. The left middle 5 is visible, but it's only visible from the right because there's a 6 here. That makes sense. The center 3 is not visible from any direction. For it to be visible, there would need to be only trees of height at most 2 between it and an edge. The right middle 3 is visible from the right. In the bottom row, the middle 5 is visible, but 3 and 4 are not. With 16 trees visible on the edge and another 5 visible in the interior, a total of 21 trees are visible in this arrangement. Consider your map. How many trees are visible from the outside of the grid? Get your puzzle input. Okay, this is a big-ass grid. Okay, let's take this. In fact, we know we're going to start with the smaller input, so let's just go ahead and grab this, copy, paste. There are no empty lines at the end. So we want to do this. We want string line equals scanner dot next line. And then what we want to do is basically we want to make like we can make a list of lists or a two-dimensional array. Two-dimensional array is probably better. Let's do int tree grid. Let's call it that. Int tree grid equals new int, and this needs to be 5 by 5, and we'll have to remember to edit that, and then we can figure out what the lengths are for this data later. For int I equals 0, and let's make 5 int width equals 5, int height equals 5, and that's normally you wouldn't capitalize it, but that's fine. Width, actually I think it's height and then width, so this should be width and this should be height. I is less than line dot length is actually probably fine. Plus I. Then we want to go, and this is actually int which line equals 0. So now we want tree grid which line I equals line dot char@, and we want integer dot parse int of this, parse int this. Wonderful. And then we want to do, what are we upset about? New string. Okay, we just have to do all the types, just every type. We got to take a character, we got to make it a character. String dot value of? Yeah, that's got to be it. Thank you. And then we want which line plus plus. So that should give us our grid. And now what we want to do is we want to start from like the top and go across. Then we want to start from the left and go across, start from the right and go across, and start from the bottom and go down. So now we need another one, which is Boolean tree visible equals new Boolean height width. Wonderful. Oh, and we probably have to do the thing where we... Do we have to make each one of these? We'll figure out whether or not I've initialized this correctly. I can't remember if I have to like insert a new array into each one of these cells or not. We'll remember that. We'll remember to do the same thing here. So now we need to go like across all of it. So for I equals 0, I is less than. So we want to do like top, bottom, left, right, top. So from the top, we basically want to be going across the heights. I is less than height. Actually, we want to be going across the width because we're going to be traversing down the height. Plus plus I. So now what we need to do is we basically need to like parse a column. So we made it so that one's the row. So parsing a column means we hold that constant and we go down this. So this actually, we're traversing across the width, and now we need to go down the height. So for int j equals 0, j is less than height plus plus j, and we're just trying to see if it's visible from the top. So now we want int tallest so far equals -1. If tree grid ij, is that right? Or is it ji? Let's think. So when we start with row 0, we want I to be 0, and then we want to check each of the j's as we go down, but the way we have it, so this needs to be ji. Man, indexing sucks. Is greater than tallest so far. We want tree visible ji equals true, and we want tallest so far equals tree grid ji. Is that right? So now we're going to be going for each one. We're going to hold the I fixed, which makes sense because we proved. So we hold the I fixed, and then we go down all the J's, and then we're good. Yeah, gross. So that's from the top, and so then that's going to set all of the things. And so what we want to do is we want to go from the top, and then from the left, and then from the right, and so on. And then we're just gonna count. So that's the top. So now we want to do the same thing. Let's just start from the bottom, and we can do the basically the same parsing. This is gonna be like 4, 5, 6 times n squared, something like that. But reading the input itself is n squared, so that's fine. So now this is equals width -1. I is greater than -1. Minus I, and we want to do the same thing. Height -1 greater than -1 minus j, and so now we're going to start at the bottom and work our way up, and we're going to do the same thing with tallest so far. So now we can take these two and we can modify them for left and right. So from the left, now we want to go across the height of it. And then we want to go across the width of it. So if we're going across the height and then the width, that now means we hold the row we're in constant and we go across that row. So all the ji's need to become ij's. And I just realized that this is going to be easier if I copy this twice rather than copying the other one. So now if we want to go from the right, it actually is kind of easier the other way. But we can at least take this part and copy it in, which is the only rough part. And then we want to take this. Yeah, that looks right. If we undo that and redo that, yeah, much better. Oh, except it now needs to be height and then width. And we can even figure out how to assign height and width at a later moment. And then we want int count equals 0 or int I equals 0, I less than width plus plus I for int j equals 0, j less than height plus plus j. Now we want to go if tree visible, what is it? I is the width, so this needs to be ji. Oh man, why did I? It's going across the height, so I can go ij just because ij reads better. Width. I mean, it all adds up the same. It doesn't really matter, but plus plus count. Trees visible plus count. And the reason we have to like mark all these things and whatever is because otherwise we'd run into problems. Trees visible 21. That is the right answer. So let's take this now. We just have to figure out our I and j. Nope. Copy, paste. Okay, cool. So how long is this? Tell me. So the width is 99 and the height is also 99. Wonderful. So let's just go back up to this. 99. 99. Okay, cool. Run again. 1711. Let's see if we did it. That's the right answer. Wow, we nailed that. Part 2. Content with the amount of tree cover available, the elves just need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left, right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. If a tree is right on the edge, at least one of its viewing distances will be 0. The elves don't care about distant trees taller than those found by the rules above. The proposed treehouse has large eaves to keep it dry, so they wouldn't be able to see higher than the treehouse anyways. Okay. In the example above, consider the middle 5 in the second row. Looking up, its view is blocked. It can see one tree. Looking left, its view is blocked immediately by the 5 right next to it. Looking right, its view is not blocked, so 2 more trees. Looking down, its view is blocked eventually. It can see 2 trees, but then it has to stop because the 5 is equal to the 5. Each tree's scenic score is then found by multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4, found by multiplying 1 times 1 times 2 times 2. However, you can do even better. Consider the tree of height 5 in the middle of the 4th row. Up is 2, left is 2, down is 1, and right is 2. This tree's scenic score is 8. This is the ideal spot for the tree's house. Consider each tree on your map. What is the highest scenic score possible for any tree? So I'm going to do an n-cubed algorithm, which is basically... no, this is still n squared, right? We're going to do 4 looks of at most n. Yeah, so we just have to iterate a little differently, which is fine. But we can take the part where we input the tree and copy that down to our second part here, and then we're just going to change some other stuff. So let's take this part. Oh yeah, wonderful. So now we've got the input trees again. We have 2 scanners, which makes life mad, but that's okay. And so now for int I equals 0, I is less than height, plus plus I, for int j equals 0, j is less than width, plus plus j. Okay. And then I want to call like some little subroutine that I write. Int max score equals -1. We know that the minimum value is 0, so that'll get overwritten. Int tree score equals something if tree score greater than max score equals tree score. Max scenic score found plus max score. Wonderful. So now we just need something to do the thing here. So I think what we want to do is we want to call a get scenic score. And what we want to do is we want to give it an int. We want to give it the tree grid. We want to give it I, and we want to give it j. And then it should be able to figure everything else out on its own. So private static int get scenic score int tree grid int I int j. Okay, and we can figure out the height and width are trivial to figure out. Int height equals tree grid dot length. Int width equals tree grid 0 dot length. Easy. Okay, so now what we want to do is we want to start where we currently are and we want to go up, down, left, right. So let's consider going up. Int current height equals tree grid I j. For int, I don't want to call this I actually. I'm gonna call this xy. Except that's not really true. This is yx because of the dumb naming convention that we have. Which makes sense. You grab a row, which is the y coordinate, and then you move along it, which is the x coordinate, which that's fine. We got 3 people in chat. Who else is here? No idea. No idea who else is here. But let's keep figuring this problem out. And let's also full screen this. So for int I equals y -1. Int up score equals 0. Int down score equals 0. Int left score equals 0. Int right score equals 0. And we'll see why we're doing it that way in a moment. I is greater than -1, minus I. We want to keep going up. So this is our traversing up. If tree grid I x is less than and let's go back and look. So for this, oh geez, it got all weird on us. So let's consider this. Can see one tree north. Looking left, it's blocked immediately, so its score is only 1, because it can see that tree though. So you do get to count the tree where it's equal to. Is greater than, and you also get to see that it's, so if this is greater than or equal to current height, then we do up score plus, and then we do break. Else up score plus. So either way, we want to do up score plus because that it always counts. So in fact, we can move that out. So this just up score plus. And you can always see stuff. But you get 0 if you're on the perimeter. So really, you can't. Okay. Stopping underneath the edge. First tree the same height. Okay. So its scenic score of an edge one shouldn't even really matter. So we don't want this to be 0. We want it to be 1 and height -1, and 1 and width -1, and that's just going to solve some problems for us. Yeah. So up score plus blah blah blah. And otherwise, we're good. So we can just do that. And so now we want to do the same thing, but for down, which is just like about iterating properly. Down. So y plus 1. Y is less than height. And this needs to be plus plus I up. So this is down score. If tree ix is greater than or equal to current height break. That is wonderful. So now we're going to do the same thing, but we want to take this up, and now this is left. And so this is going to be x minus 1, blah, blah, blah. And so this is now y I. Wonderful. And this is going to be left score. And this is going to be right score. And this is going to be right. And this is going to be x plus 1 less than width plus plus I. And we need this to be y I. And so then we just need to return up score times down score times left score times right score. Okay, so let's try running this on the little input real quick. This one. So if we take this and we put it in there, and then we change this instead of 99, we make it 5. And then we go to here and we have it run on part 2. And this is just going to sanity check us real quick. All right, tell me where I made an error. Max sanity score found is 8. Okay, cool. So that seems right. So now we come back to here, we add all this back in, we go back, we change this to 99, change this to 99, and we run it, and we get ready to submit this answer. 301,392. That seems pretty big. That's the right answer. We named it. We got rank 897 on this star's leaderboard. Let's fucking go! Hell yeah. That feels pretty good. All right, let's go. Let's check out the personal stats. 1,077, 897. We had a good day. We had a good day. This problem a little easy but we had a good day. That's our second best day after day 2, and day 2 was so easy as to be trivial. Let's go ahead and before we forget it, we're going to commit solution for day 8 before cleanup. Commit and push, and then we're going to check. Yeah. Push. No one cares. It's all fine. Unversion files. I don't. Oh, our git ignore probably is it including stuff in the out? Do we not have a good git ignore for the fact that there's an out directory? So is it just including everything? It seems like it. Maybe that's why it's mad. Okay, commit and push. Yay. That makes so much sense. Okay, cool. Let's go look at our other 2 leaderboards here. Private leaderboard view. Yeah, nobody else has even done part 1 yet. We're building the lead. We're 50 stars ahead right now. Now this person's gonna get a bunch of stars. Brian Kendall's gonna be hot in the lead, and No Hey Dev, who stopped showing up in chat, I think probably to solve these problems, is hot on our tails. But it looks like we got a good group of 5 finishing this year, which is around how many we had last year. And if we check Ryan's, oh yeah, nobody's even done yesterday's. So we're just gonna go ahead and move on there. Okay, so let's take a moment, and we gotta wait 23 hours before we get to do this again. Also, can we figure out what this is? I don't see it yet. I don't understand what this is. It's partially probably because I'm colorblind and the green ain't really standing out that much for me. Okay, blah blah blah. Wonderful. So now let's take this and put it in the level 8 problem statement, which we do, in fact, need to be able to see. So let's go ahead and look, blah, blah, blah. So day 8, treehouse, blah, blah, blah. Okay. Oh my goodness. Now it's the nice, calm part of what we do. 0 is the shortest, 9 is the tallest. I'm just assuming that that's how that needs to be. Let's move this over real quick and look. Get up to the top. Yeah. We need visible, shorter, visible interior 9 trees. Oh, no, please. Huge. Thank you. Visible. Shorter. Now left and right. All visible there in the edge. Interior 9 trees to consider. Okay. So now this part, if memory serves, so we'll go ahead and put this over here. And in fact, we don't need this section over here right now. We know how we're formatting. So this goes like this, like this, like this, like this. And in the bottom row is the last thing that's in like this. And then this needs to go like that, but we'll delete. 5 is visible. It isn't visible, blah, 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 blah. And so now we need to do height 5. Man, these long things. I just need like a little linter to help solve some of these long line issues. Visible from the top and right. And we had to bold everything this week, didn't we? It's not visible. Trees of height. For some reason the 0 is bolded, but fine. This one is visible, but only from the right. Center 3 is not visible. Height 2 between it and an edge. Yeah, I think that 0 being like that is in fact a typo. What are they doing? I mean, it's just one guy creating, you know, a completely free thing for us to all do. But does it even matter if he doesn't get that 0 formatting right? I say as I totally mangle this formatting every single week. 16 trees, 21 trees are visible. Fantastic. Your answer was 1711. We did it. Okay, on to part 2. Scroll. Okay, and so now just the word trees is visible here. That's bolded. Okay, anything in the next paragraph? No. Something about eaves, but we don't care. The middle 5 in the second row. We do have to make this into code, and then we're going to take this, add an extra line. There we go. So, like a little list here. 4. Enter, not part of the list. Can only see one tree, height of 3. Yes, yes, yes. Can only see one tree of height 5. Can see 2 trees. Can see 2 trees, one of height 3, and then the tree of height 5 that blocks its view. Tree scenic score is 4, and that can be found by multiplying that entire multiplicative equation, which all gets blocked into code. Haha. Wonderful. So now we need to do this again. Oh, beautiful. And so if we scroll, this, looking down, right, enter, not part of the list. Blocked at 2 with a height of 5. Oh, no, come on, thank you. 2, 1 tree, 2 trees, which needs to be this and bolded. In fact, many of those have needed to be bolded today, and we're just actually not going to do that. We're just going to go ahead and just accept the fact that we have not been bolding all of those things, and that is fine. Tree scenic score is 8. All of these things multiplied together. What is the height? Highest scenic score possible for any tree. My answer was this giant number. Your puzzles are complete. They provide 2 gold stars. Wonderful. So let's go ahead and look at the code real quick, see if there's anything that we need to clean up. We could change it so we parse width and height, but honestly, we just know it's 99 by 99. We can see the input. And trying to like instantiate this in the middle of the loop is gross, and I don't want to read the file twice, so I'm not going to do that. I'm just going to leave this as is. And in fact, I mean, I could just like return the tree grid given the scanner and the width and the height, but I'm not going to do that either. We're just going to leave it. So let's go ahead and do this. So read in file. Look down each column from the top. Look up each column from the bottom. Look across each row from the left. Oh yeah, and this is visible to you, but we'll make it a little bigger. Across each row from the right. Sum all visible trees. Wonderful. And now for this part, read in grid. Compute each scenic score, keeping track of the maximum as we go along. That's right. So this can just have a method comment, which I don't actually care about this. Give me the scenic score for a given for the tree at index x comma y. Cool. Compute the score, count the trees to the north of it, count the trees to the south of it, count the trees visible to the north of it, count the trees visible to the south of it, count the trees visible to the west of it. Nope, don't do that. Count the trees visible to the east of it. Return the return the 4 counts multiplied together to get the score. Okay, cool. So let's explain what we did here. So what we have is, and if we look at our problem statement, we can see this. What we have is we have a grid of trees like this, so 5 by 5. And in the first part, what we need to do is we need to go down each column or and also across each row and see which trees are visible from the outside. So when you look from the outside, you want to see like, okay, how many trees can I see? And that's basically just counting like each tree. You can only count if it's higher than all the trees in front of it. So for example, in the first row, you count 3, and then you can't see 0 and 3, but you can see 7. So you get 2 on the top row as you go across. If we go to the first column, we see 3, we don't see 2, we see 6, and we don't see anything else. So this also has a score of 2. For the second column, there's a score of 1, etc. So how do we do that? Well, we read in the file, which is pretty easy. You just grab every character, you parse it into an integer. And then what we do is we need to see the total number of trees that are visible from the outside. But if something's visible from the left and from the right, or it's visible from the left and from the top or whatever, like it doesn't count twice, it counts once. So what we do is we keep track of whether or not every tree is visible as a Boolean. And then if it gets marked true multiple times, like that's fine. That's totally okay. Because it's still only going to end up getting counted once. So we're just trying to get from a 0 to a 1, and otherwise we leave the 1 as a 1. So we just go down each column, then up each column, counting the trees just like I did out loud to you. And then we go across to the left, and then we go across to the right, counting each one. And then we just sum the Booleans that we did, which is going to give us the proper count. For part 2, if we look at our problem statement, we get down here. Now what we care about is from a particular index, if we take how many trees are visible to the north, to the right, to the left, and from below, which in our case is, it's slightly different than the counting that we did before. So instead what it is you count all the trees that are lower than it, and then the first tree that is equal to it, and that's it. So for example, this 3, we count this 5, and that's it. We count this 3 and that's it. This 5, that's it, and this 5 and that's it. But if we look at this 4, we count the 3, we count the 1, and then we count the 7, and that's the first one equal or greater. And then from below we count the 9, from the right we count the 9, and then from the left we count the 5. So 1, 1, 1, 3 is the score there. Middle file. Okay, all right. I was looking at this example and I got confused. I was like, this isn't lining up to what I did, but that's fine. So how do we do that? Well, we read in the input like we did the other time. It's pretty easy. And then what you do is for every tree that's not on the outside edge, so we start at 1 and stop 1 row below the bottom. We start at the second column and we stop 1 column from the right, because the exterior trees, they always have like one direct like if you're on the right side and you try and look to your right, there are 0 trees that you can see, so their score is always going to be 0. So anything internal is going to have a score of at least 1 because it can see the tree on every side of it, even if they're all taller. So we know that we can just ignore everything on the outside. And then what we do is we compute that score. And so how do we compute that? We literally just keep going until we find a tree greater than or equal to its current height, looking up, looking down, looking left, looking to the right, and then we multiply those 4 scores together, and we just take the highest version of that. So this is a pretty simple day. So let's go ahead and nope, we're debugging. I didn't mean to be debugging. I meant to be pushing. No, I want to commit, which is Control K, but I don't want to. Cleaned up day 8. Now let's go ahead and add all the unversioned files, commit and push. Commit anyways, I don't care about the warnings. Yes, I do love you. Wonderful. All right. And I think that's going to be it. I'm going to turn this into just a nice, real short video. And I'll see you guys tomorrow for day 9. I can't believe we're basically a third of the way through. All right. See you guys.